Okay. So today we will start current electricity. It's a new chapter, second unit. First of all, what do you mean by current? Charge per unit area? No. Okay. Suppose imagine there is a conductor, okay, a wire. I just magnified its size. It's a conductor, okay. So just imagine any cross section of the conductor. Let let Q charge passes through this cross section in time t, then the current, especially the average current t, current I, you can write in small I or capital I, is q by t. Okay. So it is over a period of time. Maybe it's over a few seconds or few minutes or few hours. Okay. You can calculate. Suppose I want to calculate current. If the current is variable, I want to calculate at a particular time. Then I have to choose the time interval very small, no? To calculate. Okay. So at a particular time, that is between t and t plus dt. Dt is very small. Okay. Here dt is very small, means tends to 0, not 0. It's not 0. Okay. The current, or generally known as instantaneous current. Okay. So you understand the word instantaneous at a particular moment. So instantaneous current I is equal to limit this t tends to 0 q by t. No, that is nothing but dq by dt. Okay. So t is the time interval. T doesn't mean a single time interval. If you can understand like this, suppose delta amount of key, some finite amount of charge crosses through any cross section in delta time t. So average current is delta q by delta t. Okay. And at a particular time, that is between t and t plus dt, such that dt tends to 0, the current, that is instantaneous current, is limit t tends to 0 q by t. Okay. Or we write dq by dt. So this is known as current is when we take derivative with respect to time, we say time rate of flow of charge. No, time rate of flow of charge. Okay. Okay. So it has to be through some cross section, whatever may be that cross section. Okay. We say current through that cross section. Okay. Then, so what's the direction of current? Current is along the direction of flow of positive charge. Okay. Okay. And is along opposite to the direction of flow of negative charge. Okay. Flow of negative charge. Okay. This is just for convention. It doesn't mean current means something is flowing means current. Okay. something is flowing, there is water current, air current. Okay, so similarly here we consider charge current. We take positive charge flow of positive direction of flow of positive charge is the direction of current. This is just conventional, so we call it, it is a conventional current. Okay, in this convention it is defined, that's all, there is no more extra meaning to this. Okay, and types of current. Types, there are two types of current. Two types. First one is steady current, STEADY, steady current. So the word as it is meaning, you know, it's not changing over time. No, means if I draw a graph, this is time axis, this is current axis. So current is always at the same value each time. So this is nothing but steady current. Okay, this current we know, DC current, no, direct current. So this type of current from where we get, when you connect a battery to a circuit, the battery gives a steady current. No, okay. There is another type of current. No, not alternate. There is variable current. Part of that is alternate. The second is variable current. Variable current. Okay. What is that? For an example, suppose uh, similarly this is the time axis, this is the current axis. Okay, I'll draw a line, dotted line, and this is suppose 2 ampere. Suppose this is 2 ampere current, always 2 ampere current, and this is 1 ampere current. This line is 3 ampere current. Suppose current is changing its magnitude like this, starts from 2 ampere to goes to 3 ampere, then drops to 2 ampere, then drops to 1 ampere, then again follows the same path. This is variable current. This is variable current. Current is not changing its direction here. Like a battery, if I have some circuit, a resistor is connected to a battery, so current is always here, it will be always clockwise and same magnitude. Here also, suppose I have some variable current source, somehow I can vary, there is some resistor connected to it, the current is in same direction, it is not changing its direction. What happens, it changes the magnitude only. Okay, so this is variable current. In variable current, there is one type of current that changes its direction periodically. When current changes its direction periodically, let's draw its graph. This is T, this is I, this is 0. So current, this is 1 ampere, this is minus 1 ampere. It changes like this. No? So it starts from 0, goes to maximum 1 ampere in one direction, then it drops. Current direction is not changed. When it becomes negative, means current starts flowing in the opposite direction. Okay, this is our alternating current. This is the current supplied to our home, no, AC current. No, using AC current we run our AC. No? Yes or no? What is that? Yeah, no. Air condition. To run AC, we need to pay from our AC. What is that AC? What is that AC? Account. So three are related. Na? SC to SC to SC. Okay. Okay. You need this SC to buy this SC, and to run this SC, you need this SC. Okay. Okay. So we studied variable current and through any cross section. Okay. And instantaneous current or just current at any time. Then types of current: steady current and variable current. In steady current, this is the DC current which a battery supplies to a circuit. Variable current, this is the variable current which changes its magnitude with respect to time, that is variable current. But one type of variable current that is periodically changes its direction. It changes its magnitude as well as direction, that is alternating current, periodically changes. Okay. Okay, then units. What is the unit of current in SI? Coulomb per second. Okay, that is ampere, no? But ampere is our fundamental quantity, ne? Ampere is our fundamental unit. Okay, current is the fundamental quantity, so ampere is its unit, is fundamental unit. Okay, so actually coulomb is ampere into second. Coulomb we take, coulomb is the derived quantity. Oh. So what is 1 ampere? 1 ampere of current is that current, nahin, a current through what, flowing through a conductor. A current flowing through a conductor is said to be 1 ampere. Current flowing through a conductor is said to be 1 ampere if 1 coulomb of charge flows through any cross section in 1 second. No, this is 1, this is 1, so it will be 1. 1 coulomb of current flows through any cross section in 1 second, that is 1 ampere current. This is the simple definition of 1 ampere. Then CGS unit, 1, it is stat ampere. Okay, that is equal to 1 stat coulomb divided by 1. What is the CGS unit of second? Okay. Second is dawn. It don't like to get changed in any unit. It is always second. Whichever unit you choose, it is second. Okay. Okay. Start. I use the word start. So this is a specific CGS unit. A specific CGS unit where I use start. That is electrostatic unit. Okay. This is electrostatic unit. ESU. ESU is a CGS unit that is known as electrostatic unit. That is charge at rest. That what we studied in first unit. Then there is another type of unit, electromagnetic unit. Electromagnetic unit. Okay. In that unit, it is known as short form. It is known as EMU. Okay. Here the unit of current is 1 ampere. Ampere. Okay. That is 1 coulomb. by 1 second. Okay. 1 coulomb is equal to 3 into 10 to the power 9 stat coulomb. 3 into 10 to the power 9 stat coulomb. If you use this relation here, that means 1 ampere will be 3 into 10 to the power 9 stat ampere. Okay. 1 coulomb is equal to 1 by 10 ab coulomb. Okay, so ab coulomb is a larger unit, but start coulomb is a smaller unit. Okay, so here if you use here, so 1 ab ampere is equal to 1 by 10, 1 ampere is equal to 1 by 10 ab ampere. Okay, is it okay? Start coulomb 1 ampere is equal to 1 by 10. So this is all about current, and we know current is a scalar quantity. No, one thing I just missed, current is a scalar quantity, we know, though it has both magnitude and direction. No, we can define this, it has a direction clockwise or anti-clockwise. We are defining some direction to the current. No. So despite having both magnitude and direction, current is a scalar quantity. Okay, why? Because where should I write? Let's write here. Because it does not obey, what obey? Vector law of addition. Eh? Vector law or law of vector addition. Law of vector addition. That means if a wire has, this wire has 2 coulomb charge, another wire has here 3 coulomb charge, whatever the angle between these two currents, the final wire will always have 5 coulomb charge. No? It's added algebraically, not vectorially. Okay. Okay. That's why it's a scalar. Though it's a scalar, we define it for our, if there is some necessary, then we sometimes define its direction and define it as a vector sometimes. Okay. This is up to us. We can make an area also a vector. First we studied area is a scalar quantity in 11th standard, then we make it a vector in 12th standard. No? By assigning some direction. Okay. If it is a plane air, it should have some direction. Okay, some positive side, some negative side, depending upon its the boundary, how the boundary is traversed. Okay. Okay. Similarly, sometimes we also define current element, positive or negative. If you can define a particular direction, then we define it as a vector quantity. Okay. But but normally you can say this thing. Okay. Normally you can say this thing. Okay. When we define it as a vector quantity, then its property will get changed. The way we define it, in that case, that has to be follow this law of vector addition. Okay, we'll discuss that one, but just remember this one. Okay. Okay. So I will erase. No, I'll clean the board. Okay. The next term is current density. Current density. J vector. It's a vector quantity. Huh? It's a vector quantity. Okay. Suppose similarly, just imagine I by Q. No. Current density. Current by area. So similarly, you just draw a small area at a point P inside a conductor. Suppose this is my conductor. It's a large conductor. It is going this way, this way. So current is flowing. So charge is flowing in this direction, means current is flowing in this direction. Okay. I have to calculate density somewhere here. This point, this is a point P. I'll draw a small area delta S such that the area, the finite area delta S at P is perpendicular to the current. Okay, is perpendicular to the current. Okay. The current that is passing through this area delta S is delta I. Okay. Suppose delta I current is flowing through delta S. Okay. So the average current density J, this one, average, I'll write J, a line over it, it means average. Okay, is equal to delta I by delta S. Okay. Okay. So the area surrounds the point. The area surrounds the point. If I want to calculate the current density at P, current density at P, then I cannot make that much area. No, I have to reduce the area to very small size. No, at P, then we need delta S should tends to 0, so that we will have a point like area. No? So delta S, when it will get reduced in size, so we can say that it is just at P. So in that case, current density, only current density, so no average, current density at P is equal to limit delta S tends to 0, delta I by delta S, that is di by ds. Okay. When we use d, means it's infinitesimally small. Okay. Okay. Yes. That means the area has to be perpendicular to the current. Area has to be perpendicular to the current. If somebody draws this area, draws the area like this, not like this. If he draws, suppose this is the point, another point P, he draws like this area. So what will happen? The area, so either area get less or current flowing through that point will get less. No, that will change. That means that will change my current density, but I am not changing anything. I am not changing the current. So how will current density change? Okay. So Then what do I have to calculate? I have to calculate the component of area, that is perpendicular to the current. Na? So component of delta S perpendicular to current I, or you can say component of delta S vector parallel to I, isn't it? Because its delta vector is this way, this direction, and this is the current direction, it is the angle I. So this is delta S vector, its component is delta S cos theta. Okay. Okay. So this is not average current anymore. Okay. I don't need to give sign average current. Okay. So J will be delta I divided by delta S cos theta. Yes. Understand? Okay. So that means current delta I, or you can let di by ds cos theta, whatever. Okay, so delta I will be J delta S cos theta. Two vector, we can make these two vector quantities, and product of those two vector quantities gives a cos theta. That means it should be multiplied J dot. There is a dot product between them. J vector dot delta S. So my current is the product of two vectors, and their product is dot product. No, their product is dot product. So we know the resultant of dot product is a scalar quantity. Okay. Delta I should be a scalar quantity. In this way you can prove. Okay. If you have to find the current over a large area, then current over a large area, you just integrate this J dot ds. J dot ds. This will be the formula. Okay, over area, any area, any finite area, finite large area. Okay. So till now we studied about current and current density. Means charge is flowing. Current is there means charge is flowing. But which charge is actually flowing? We are considering conductors. Who are the charge carrier? Free charge carrier. Inside conductor, who are the free charge carrier? Atoms. Yes, it's the only free electrons. Okay, it may have, you can take any atom, suppose sodium, it may have 11 electrons, but all electrons are not free. Only one electron per atom is free. No. Similarly for iron, maybe it's one or two electron is free. We cannot say that all the electrons are free. Okay, that means those charges which are not bound at a place, which are not fixed at any point, they can carry the charge. But it is so easy, they will move easily. We know current is flowing, means electron is flowing. That means if this is a conductor, this is my conductor, if current is flowing in this direction, means electrons are flowing in the opposite direction. This is the conventional current, opposite to the negative charge motion. Current moves in the direction opposite to the negative charge motion. So electrons are moving from higher potential to lower potential. Charge is flowing in this direction, means this is your higher potential, this will be your lower potential. Na? if this side is potential V1, this side is potential V2, then V1 has to be greater than V2. V1 has to be greater than V2, so current will flow from higher potential to lower potential. Okay, but the electron flows from lower potential in the opposite direction of electric field. Okay, electric field is in this direction, so electron flows from lower potential to higher potential. Okay, when few electrons are removed from a atom, so rest thing is a ion, na? Those are positively charged ions, no? So in atoms there are ions which are arranged in a particular pattern. Okay, not completely randomly. Ions are arranged in a particular matter. Okay, so these are ions. Okay, so these ions are we called lattice points. Lattice points, you can remember this word, lattice points. Okay, these lattice points do not move, but one thing they can do, they vibrate staying at their place. No? They can vibrate in any direction. They vibrate due to thermal energy. Okay, when an electron tries to move, it has to encounter with the lattice point and rarely with other electrons. Okay, rarely with other electron, but mostly they interact with these lattice points. Okay, their flow gets disturbed always, frequently. They cannot move through a material, through a conductor easily. Okay, but remember, electrons are moving at a very large speed inside a material. If it is a material, I'll draw again. Electron are moving. Suppose this is an electron, it is moving like this. Random motion. They collide, change their velocity. They collide, change their velocity. Okay. But after a very long time, if you observe, their net displacement is zero. I have not given any potential difference. So they will not get any force. They are not getting any force to move in a particular direction. So their motion is completely random. Their net displacement will be zero over a long time. Okay. Even if you consider any small area for a some interval of time, you will find that the average number of electrons crossing the surface area through this direction will be almost equal to the number of electrons crossing in the opposite direction. So net current is zero through a surface when there is no potential difference is given. Okay. Okay. So when there is no potential difference, no drift velocity, no flow of current. Okay, but but what happens when we give a potential difference electrons? When we give a potential difference, let me draw. Potential difference means we will give a electric field. Its potential V1, its potential is V2, this end V1 is greater than V2. Now electrons moves somehow like this. It moves can you figure out what I am doing? It is random, but over time it is gradually in a particular direction, right? So we can say it has a net speed opposite to the field. No? There can be a current. Now it shows there is a current. Okay, but still their motion is very random. No, it's not smoothly passing through the nucleus. No? and this speed is very high. It's comparable to light speed. Electron speed is in the, I think it's in lakh kilometer per second. Like light is 3 lakh kilometer per second. Not like that, but it is comparable. Comparable. Very fast. They are moving very fast. But this drifting is small. This drifting is small. Okay. When suppose this is a lattice point, when electron interacts with a lattice point, either it will have the same velocity in this direction, it may happen maximum, there will be no change in direction, or it can, suppose it's a drift speed, its speed is Vd in this direction, or it can just rebound in the opposite direction Vd. So plus Vd minus Vd, it has both possibility, right? If it is going with Vd speed, after collision, it after interaction, it may have the same Vd speed, or it may have the Vd speed but in opposite direction, right? So it varies after a collision, it varies from plus Vd to minus Vd. After a collision, varies from plus Vd to minus Vd. So what can I expect? What is the average speed after collision? So what can I expect? Average speed after collision? It's average. Add these two extreme divided by 2. If you add them, it will become 0. Yeah. So we can take that at average, not that it is always becomes 0 speed, but average is after collision its speed becomes 0. Okay. And this speed of the electron is known as a drift speed. Drift speed. I used to call it drift speed, but you will find in your book it's written drift velocity. Okay. Drift velocity. Okay. So it's up to you. You can choose, say whatever you like. Either you say drift speed or drift velocity. Okay. DRIFT speed or drift velocity. Because a wire, conductor wire is not always straight line, it may be bent at several points, so we cannot assign a particular direction. Okay, so better we, if you use the word drift speed. Okay, some text, some books also use speed. Okay, not velocity. Okay. Okay, so in school, in your NCERT book, it is written drift velocity. If you go to SC Verma book or few foreign author books, you'll find they have written drift speed. Okay. Okay. So how can we define this drift speed? Suppose you understand this phenomenon, what is happening inside the material. No? Suppose an electron gets drifted through a distance L in time t, opposite to the electric field, opposite to the applied electric field. Suppose an electron get drifted through a distance L in time t opposite to the applied electric field. Okay, so then drift speed can be written as Vd is equal to speed is distance by time. Okay, Yes. Okay. So that means electron is moving under the electric field, means it should have a, it should experience a force due to this electric field. So what is the force on the electric field? Force on the electron, F E is equal to minus QE. E is the electric field. Charge is equal to minus Q or minus E. I can write minus E. No. Okay. I know the force. Then what should be its acceleration? If it experience force, means it should accelerate. So accelerate, huh? Acceleration. That is force is equal to acceleration is equal to force by mass. Right? Acceleration, acceleration of electron. Okay, only magnitude. We are writing only magnitude. We know where it is going. So acceleration A is equal to force by mass of electron, that we can write E by M. So just I am using magnitude, so I remove the negative sign. We know it is going in opposite direction of electric field, so force, that's why it's written minus C, or similarly you can change charge is negative charge, so I have given, that's okay. We know its direction, so if we assign its direction, so no need to give any plus minus sign, okay, for vector quantity. Now there is another term, remember, relaxation time. So capital T, I will remove this one, this part of it. There is a term like a relaxation time, that is, I use tau, that is average time interval between two successive spelling. I am forgetting the spelling. SUCC, now. SSI, successive collisions. That is not, I am telling that is bit time between two collisions. It's a average time interval. Okay, average time interval between two successive collisions. Okay, successive means just next to next collision. This collision and its next collision. Okay, so that is time tau. Okay, so within that time, within that relaxation time, electron will get time to accelerate. After that, when it collide with the lattice point, interact with the lattice point, its average speed will become again 0. No. Then after that it gets tau time to get accelerate. Then it, after collision, its speed again becomes 0, average speed. This way it moves. Okay. So you know acceleration, you know time. So how far the electron will go in this time by this acceleration? The distance, I mean the distance covered by the electron, or by the electron in time tau. You know, we know a formula, S is equal to ut plus half at square. Yes, u is the initial speed, means just after collision, that is 0. No, t is our relaxation time tau. Acceleration we know, acceleration is equal to E by m. So substitute it, we know S, in place of S we have written L. So L is equal to This part is 0 plus half A is E by M tau square. Is it okay, or do you find any mistake? In your book, they have used another formula. In your book, they have used another formula, that is V is equal to U plus AT. They have taken, this is average velocity. Initial velocity is 0. This is average velocity. So acceleration, since this is 0, acceleration E by mt. Okay. So they have used this formula. But instead of using this formula, I think this is more appropriate, but I don't know, there may be different logic, but I have used this formula because it will accelerate within the time tau. That will start from 0. This is the final velocity after tau time, right? This is the final velocity after tau time. It is initial velocity, this is final velocity. I am not calculating final velocity, I am calculating average velocity, because this is average relaxation time. From here drift velocity you will get. So we know drift velocity L by T. So drift velocity that is Vd is equal to L by tau. So if you divide one tau, L by tau, so you will have E by 2m tau. Right? There is only a 2 in the denominator compared to this. Okay? It will not matter much. Okay, every other variables are as it is, only there is a half difference. Okay, this is my drift velocity. Okay, this is my drift velocity. I think I will insist you to write this expression. If I calculate, this should be the maximum drift velocity, maximum average, but this is the average drift velocity. So if it is drift velocity, then we know drift velocity depends on Vd is proportional to electric field. The more the electric field, that means more the potential difference, more will be the drift field. Okay, the faster will electron move, this E of m, this thing we cannot change, so we cannot say Vd depends upon the electron charge, because we cannot change the electronic charge. No? We cannot make it 3.2 into 10 to the minus 19 coulomb. So it is not meaningful to say that Vd is proportional to E, because E is not going to change. Then how Vd will going to change with E? Okay. So basically two factors, it depends, Vd and tau, relaxation time. More time it gets between two successive collisions, its speed will be more. Okay. But remember, tau is inversely proportional to temperature. This is temperature. Why? If we increase the temperature of the material, these ions will vibrate more. If they vibrate more, they will interact with the electrons, drifting electrons more. They will obstruct their path. Okay? They will obstruct their path. They do not easily let the electrons move. Okay, there will be more resistance. So in that case, if temperature more collisions, so if temperature increases, more collisions happens, mean relaxation time will decrease, frequency will increase, means relaxation time will decrease. If relaxation time will decrease, drift speed will decrease. Okay, finally it will affect the current. finally it will affect the current. So temperature increases means drift speed decreases. Okay, so it is not directly, it depends on the temperature, but we can see the temperature dependence of Vd. Okay, uh, just take if you want you can take a note, but maybe it is already available in my note. Okay, this thing is only extra, or most of things you can get in the note. Okay. Huh. One more point. When the last time I have gave you some questions. Okay, no, set of questions, and I asked you to answer them. Okay, first you prepare and answer them by sitting, by not following any material. Okay, so you answered most of thing, but thing is that you have to be have something written about your figures, the quantities you are using, you should have a writing on them. Okay, you just need to explain something in your text, in your reply. Okay, otherwise it will make you feel like what, desert like feel, desert or desert, sand only, no greenery. Okay, even if you think you have written the answer, but mark will get deducted. Okay, the examiner will not be happy to give you mark. Hmm. So next time try to improve your writing. You just explain the thing. If I give you current density, okay, you just explain the thing. Okay, it's a vector quantity. Oh, step by step you write it. Okay. Just